starting recording and transcription. And I am letting everybody know that you are being recorded right now. Sweet.
Woohoo!
So last week, questions that we did were we focused mainly on the difference between diffusion and osmosis, with all that kind of stuff moving around. We had the different types of transport. We reviewed those. And then a little bit of action potential kind of stuff. Sodium, potassium, ATPase. If you go back and watch the other video, I said this probably 30 times. Know what sodium, potassium, ATPase does, because it is a test question every time. In case people don't remember from last time, it's always a question. Okay. This first chunk of questions is going to be finishing up keeping with the week 1 material of the action potential. What did Dr. Tate get to today? What did he cover?
He stopped before he started action potential, so I'm assuming he's doing action potential Thursday.
Okay.
Not for us. We had to listen to it all anyway.
Let me... Come on. Open with... Come on. Gosh, I need a new computer. So he got... through membrane stuff, kind of got to here.
Yes.
Okay. Any questions or things that were confusing?
Yes. I noted them in my notes. Let me look through.
Like I go over all of this in those smaller videos, but just in case there's something that he says that's different,
The
let
only
me
thing
know
that
so we can...
the only thing it looks like that I really noted, because I did it big and bold and red, was details, detailed steps for the sodium, potassium, ATPase. He's like, I'm super big on the details. You need to know these. And I'm like, and then missed the entire, he confused me when he was explaining it. So I was like,
So this little chart?
Yeah,
right here?
that right there. As he was going through it, he just confused me, but then was like, you need to know every detail of this. So
Okay. So my best guess would, because the sodium, potassium, ATPase doesn't really have a lot of steps. Maybe just a couple of the abbreviations and a couple little things. Okay. So for example, you have the sodium, potassium, ATPase pump right here.
Mm-hmm.
Big rule that we always want to understand: 3 sodium go out of the cell, 2 potassium come into the cell. That's the overall main idea, and it uses ATP in order to do that. So our sodium, potassium, ATPase starts its open towards the inside of the cell. This is the inside. And we call that the ICF. That's intracellular fluid.
That was the other question I was going to ask you, was ICF and ECF, because he kept saying that but didn't explain what it was. And so I was like, okay,
ICF is the intracellular fluid, so the cytosol and the fluid and stuff that's inside of the cell, versus the ECF, which is the extracellular fluid. So all of the fluid and stuff that makes up this space outside of the cell.
So because is the ECF and extracellular matrix basically the same?
Yeah, so the extracellular matrix, all of this gunk. Yeah. So we have the cells, and then all of the stuff outside of the cell. All of this stuff is floating, conjoined together, all that kind of stuff, with fluid. Okay. So that's why water, we're 70-something% water.
Yeah.
So within our ECF and our ICF, we have liquid and everything, and like the liquid and the water and the hydrogen bonding and all that kind of stuff is what holds kind of all of this gunk together.
Okay.
So
Okay.
that fluid that's with all of this stuff mixed into it is the extracellular matrix. And when we just specifically talk about the fluid component of it, we talk about extracellular fluid.
Okay.
Same thing on the inside of the cell. There's a ton of proteins and stuff all floating inside of the cell. And so that the fluid component of it we call the ICF, or the intracellular fluid.
Okay.
Yeah, and that's not something typically professor that you see a lot more of ECF, ICF stuff in tries 3 and 4. You dive more into that kind of stuff, but here, just so you know those abbreviations. So, okay. So 3 sodium from these, and we also mentioned before, I always like to talk about the cell being a banana in the ocean. Did I mention this last time?
I don't think so.
Okay. I always remember that there's a picture in the other slides, in Dr. Van Winkle's slides, that literally has a banana floating in the ocean. Because bananas, as we know, are high in what?
Potassium.
Potassium. So the potassium is high on the inside. And the ocean has lots of what in it?
Salt or sodium.
Salt, which is sodium. So potassium is supposed to be on the inside of the cell. Sodium is on the outside of the cell. The banana in the ocean. So, and this will make a lot more sense once we talk about action potential stuff, once you go deeper into action potential stuff. But during the action potential that occurs, a buttload of sodium comes into the cell and a bunch of potassium leaves the cell. So the job of this sodium potassium ATPase is to write that process. So it's going to be bailing out the sodium and letting that potassium back in to reset the cell.
Okay.
So first step, the sodium comes in and it binds onto 3 specific sites for sodium, and that's from the ICF, or inside of the cell. Then we have an ATP bind, which then, it phosphorylates. It breaks off one of the phosphates to release energy, and that binding of the phosphate causes it to change. So it closes on the inside, opens to the outside. The sodium leaves, and then the potassium can come back in and bind, and then it causes it to reset. So, and it does this over and over and over and over and over again.
That's a whole lot simpler than what he put it. Because
yeah,
I had no idea what he was saying.
Yeah. There's a lot of like big words and stuff, like kind of more the sciencey words that he's going to use in here, like the high affinity binding. Just if we think back to Biochem 1, something that has high affinity just means that it really wants to bind to it.
Yeah.
Meaning that it's really likely that it's going to grab and bind something there for whatever it's high affinity for. So.
Okay.
Yeah. Biggest things to remember: ICF, ECF. Sodium is going to go out of the cell, go from the ICF to the ECF. That's a way he might phrase that question. We use ATP, and then there's high affinity for potassium that goes from the ECF into the ICF. Yeah.
Okay.
Does that make more sense?
Oh yeah, way more.
Stick. Dope. If you didn't watch the video from last week, I think you mentioned that you hadn't. Go back through. I go through all of these questions on that.
Okay.
As well, I will I'll post this document after we're done today. I'll post it in the chat so you can download it as well and look over it.
Okay.
Okay. Additionally, let me actually pull up, because last week we made this picture, which this is going to help immensely for Thursday. And as well, you can edit it while he goes over this stuff. This is action potential stuff. I walked through the action potential very step by step. So I'll throw that in the chat so that way next lecture on Thursday, you'll have that. And when you go back and watch last week's stuff, every professor likes to teach it a little bit differently because there's a lot of different charts and graphs that have things slightly different on each one. So just tune it to whatever Dr. Tate specifically says. And that's how you should be tested on it.
Cool.
Okay. We're going to go through these questions. As we go through them, we can discuss. I think what we're going to do, we're going to go through each of the answer choices. It's going to be, just because you haven't officially talked about this in class, I'll do most of the talking. And we're just going to kind of go step by step, go through each answer choice, why it's either wrong or it's correct. And then as questions come up, ask questions, and we'll dive deeper and go into more explanations of stuff. Sound good?
Sounds good.
Okay. So during the resting state of a neuron, which of the following is true? Before we answer the question, when we say resting state, what does that mean? What do we think resting state means?
Polarized.
What was that?
Neither polarized nor polarized.
Yeah, there's not polarization or depolarization occurring. We sit at a specific charge known as the resting membrane potential. You guys remember that word? We've talked about it. We talked about it a little bit. Yeah, resting membrane potential. Do you remember what it is for a nerve cell?
-70 millivolts.
Yeah, good. What protein's job is it to maintain the resting membrane potential? What's the name of that protein? Give you a hint. We just talked about it. Yeah, that's right. The sodium potassium ATPase.
Oh, I was like, huh? I'm so confused.
The sodium potassium ATPase, one of its big jobs is to maintain the resting membrane potential, because we do still have some, we call them leaky channels. Like there's all the different types of channels, the voltage gated channels, the ion channels, all that kind of good stuff. There's something called leaky channels, which are channels that are open all the time. It's passive diffusion. And we get a little bit of trickle in of like sodium and other ions and stuff leaking in and out of the cell just slowly. So that's why, the sodium potassium ATPase is always on gear and doing its job. Okay. So during the resting state, sodium ions are actively transported out of the cell. Immediately, we know that's a no, because that is going to be... Actually, hold up. Granted, these questions are also from GPT, so some of them are going to be a little bit off, and it's mostly... I think these questions will be trickier than what Dr. Tate will give you. So, sodium ions are actively transported out of the cell. Technically, this is true, because like we just talked about, the sodium potassium ATPase is active all the time to maintain the resting membrane potential. We're going to look through the rest of the answer choices and see if there's potentially a better answer. The inside of the cell is more negatively charged than the outside. This 100% is true, because remember, we have on the outside of the cell, We have a lot of potassium, and we also have chlorine, Cl. That's outside of the cell. And then inside we have potassium, which is positive, and a whole bunch of amino acids and proteins, which are very, very negative. Lots of protein on the inside. Overall makes the inside of the cell very, very negative. Potassium ions are actively transported into the cell. Again, technically true because of the sodium potassium ATPase. And then the neuron is unable to generate an action potential. If we're sitting at resting state and nothing happens, so as long as there is no stimulus, there is no action potential. With this, I was put technically all three of these answer choices are correct. What is the most correct, I would say, is B in this case. But again, if you had this question on a test, you could easily make the argument for any of these three being true. Okay. Any questions arise or come up from this?
Nope.
All right, moving along. What occurs during the depolarization phase of an action potential? So really quick. I wish I had like a pad that I could write on, but our action potential chart, we have resting membrane potential, stimulus, it hits threshold, we get our beautiful little spiky, comes back down, and then goes back there. This spot right here is our threshold. This is our -70. Sick. So our steps, we have resting membrane potential, then we have a stimulus, and then we have sodium channels. Thanks due to the stimulus, we have sodium channels. Let sodium into the cell. As soon as we hit threshold, we get depolarization. Thanks to voltage-gated sodium channels. And the voltage-gated sodium channels are open all the way until the very, very top. And those voltage-gated sodium channels close. And then we have voltage-gated potassium channels open. And we get repolarization. And then it goes past resting membrane. So we have hyperpolarization. Our potassium channels down here, those potassium channels close. And then we get back up to our resting membrane potential. This was super quick, super sloppy, just covering the general stuff. In the picture that I put in the chat, as well as in the previous video, I walked through this in a lot more detail. There's a lot more to find stuff here, as well as listen to Dr. Tate, see what details he specifically gets into. Personally, I'd recommend it might be better to just watch the recording. With some teachers, especially teachers who aren't super used to lecturing or don't have a really good flow with lecturing, sometimes they'll jump back and correct themselves. And sometimes it's really, really hard to follow. Yeah, exactly. Follow along with that. It's better with the recording that he can say, oh, wait, hold on, that's wrong, and jump back and re-say what he said. It gives you a chance to back up the video and be like, okay, hold up, what was wrong? Back up the video and rewatch it to clearly understand what he was correcting and what he wants you to know. So putting this off to the side, so we have it here to look at. What occurs during the depolarization phase of an action potential? The inside of the cell becomes more negative. This is 100% false because a crap load of sodium is coming into the cell, right? and we're literally getting more positive during depolarization. Potassium ions exit the cell. Nope, because that is during repolarization that is occurring, not depolarization. This is why these words, definition-wise, are super important to understand. Sodium ions enter the cell, making the inside more positive. That sounds right to me, just like we talked about. And the neuron returns to its resting state. Nope. This is going to happen after repolarization and after hyperpolarization are completed. Real quick, when we talk about this, that initial stimulus, we start to get to threshold. What's the ion responsible for that?
What do you mean?
What ion enters the cell to get us to threshold?
Enters the cell?
Yeah.
Sodium.
And again, you guys haven't learned this, so it's okay if it's still confusing.
Yeah, I have no idea.
It's going to be sodium.
Yeah, that's right.
Yeah, here at the very beginning, most of the time, we're going to be dealing with sodium.
Okay.
This stimulus right here. Most of the time, we're just going to say it's due to sodium ion channels. If just regular sodium ion channels isn't an answer, you can also look for stuff like leaky channels. Later on, when we talk about the heart, they'll call them leaky channels or leaky sodium channels.
There's
Funny channels.
What was he calling? He said leaky channels so much today that I wrote it down.
Yeah. So
the ungated ones that are always open.
Yeah, exactly. So the leaky channel, you could also say ungated sodium channels is another way to say it. Any of these names you can use for this. All these are these are open ion channels that stay open that let ions pass through.
Okay.
So they're super, super, super important when
And
we talk about.
They're specific to the ion, right?
Yeah.
So
they're still going to be specific to the ion.
Okay.
Because the channel itself has a specific shape.
Mm-hmm.
So because it's a three-dimensional thing, so it's going to have a shape. It's like a hole through it.
Okay.
And that shape is going to change depending on the channel.
Okay.
And each of the molecules that we want to have pass through are also going to have a specific shape and structure and charge and all that sort of stuff.
Okay.
So just like enzymes, how enzymes are super specific, our ion channels are also super specific.
Okay.
Yeah. So all of these guys, leaky channels, funny channels, the ungated sodium channels, any of these kind of stuff, these answers, this is how we get to threshold. Whenever there's a stimulus that occurs, that's how, thanks to these types of channels, and a couple of others that's a little bit above our pay grade right now that we won't worry about, is how we can get a stimulus to threshold. As soon as we hit threshold, we dive and get way more specific. I'm going to keep going in the questions and see. We might have a couple questions about that. But if not, I walked all through it in the previous tutoring video, as well as in the recordings. Kind of walked through those steps and what's occurring there. Okay.
Cool.
Okay, so the threshold potential is the membrane potential at which of the following occurs. So the neuron is hyperpolarized. Nope, that's going to be happening here in this chunk. This is hyperpolarization down here. Sodium channels begin to close. Again, this is a big nope. This threshold is where I'm going to be very, very specific here. And if this doesn't make total sense, we can talk about it. Threshold is where the activation gate of voltage gated sodium channels open? It's a lot of words. Any questions about that specifically?
Not yet.
Okay. We did talk about activation gate a little bit like 2 weeks ago.
Oh, so that sounds vaguely familiar.
Yeah.
Vaguely.
We're just gonna touch on it. I go more into it in the video. An activation, a sodium channel, a voltage gated sodium channel is kind of built like this. It has two gates. It has one here and then one at the top like this. We have an inactivation gate and an activation gate. Okay? Inactivation gate, activation gate. When we're at resting membrane potential, so at resting membrane potential, the activation gate is closed, just like that. As soon as we hit threshold, actually, let me do this. This is purple all the way through until here. As soon as we hit threshold, the activation gate snaps open, just quickly, boom, pops right open, and sodium rushes in.
Okay.
And that happens right at this point right there.
Okay.
Okay. So look for this. Dr. Tate will probably go into this a little bit as well on your guys' next lecture on Thursday. So this right here, we said no because it's the sodium channels they open, they don't close. Potassium channels open. Nope. Again, the potassium channels are going to open towards the top of depolarization. Okay. Listen to what Dr. Tate says specifically when they open. The graphs and the charts that I've seen at, so at 0 millivolts, they start to open slowly, is what I've seen. So we typically go to about 30. So this is 0 millivolts. We typically go over a little bit. The graphs and charts that I've seen, it's around the 0, somewhere in here, that the voltage gated potassium channels start to open, but they open really slow so that they're not open until we reach the very top here. Okay.
Okay.
And then an action potential is initiated. That right there, that's going to be our golden answer. As soon as we hit threshold, action potentials have something that's called all or nothing. Okay. As soon as we hit threshold, there's going to be an action potential no matter what happens. Granted, something super extreme like the cell gets obliterated or something weird like that, but like normal physiology, if we hit the threshold, we get an action potential, we get a message sent. If we don't hit threshold, we do not have an action potential. No matter how close it is to threshold, if we don't hit threshold, nothing happens. Okay?
Okay.
That is typically a test question where they're like, oh, you have this stimulus and this stimulus and this stimulus and this stimulus. Doesn't matter. If they don't hit threshold, nothing will ever happen. What happens during the repolarization phase of an action potential? So we talked about this. We said repolarization is when we're coming down. This is when those voltage-gated potassium channels are open and potassium is leaving the cell. So the membrane potential, becomes more positive than the resting potential. Let me make sure. Yeah. Okay. The membrane potential becomes more positive than the resting potential. During the full repolarization phase, the membrane potential, remember, we're going down. So because we're going down and we're going to hyperpolarize, we're going to say that that's not the case because we're going more negative, and we're actually going to go more negative than the resting membrane potential. Sodium channels close and potassium channels open. Just from off the bat, I'm going to say that that's probably going to be our best answer choice because, like we just talked about, those voltage-gated potassium channels and the voltage-gated sodium channels are closed. Voltage-gated sodium is closing, and voltage-gated potassium open. The neuron becomes refractory to further stimulation. I don't love this, the wording of this, but it's a good chance to explain refractory. There's something called an absolute refractory period and then a relative refractory period. Again, we talked about these, touched on these briefly before. You remember a little bit of tickle in the brain right there?
Yeah, and I remember Dr. S touching on them at the end of last try too.
Yeah. So the refractory period, and again, like I said, these are AI generated questions, so they're not perfect. So this is technically as well, this could be a good answer choice for it. Refractory period, what that's referring to, refractory is referring to the neuron's ability or the cell's ability to generate another action potential.
That's right, because absolute, it doesn't matter how strong it is, it won't happen. And then
exactly,
relative, a super strong stimulus could make another action potential happen.
So okay. Our absolute refractory period is from the time as soon as our action potential starts, we have those voltage gated sodium channels open, our absolute refractory period starts. And it's going to last until we reach back to threshold on the other side. Because once we hit threshold again, remember I talked about these two gates right here on the sodium channels? Yeah. The voltage gated sodium channels. And when we get back down to threshold, these are going to reset. So right here at this point, when we reach threshold, the voltage gated sodium, the activation gate, this top gate, snaps open and sodium starts rushing through. As we get more and more and more depolarized, the inactivation gate, coming here, this orange line, we're coming in through here. The inactivation gate starts slowly closing. It closes right here at the top. And then as soon as we hit threshold again, this point right here, both of the gates snap back to their original position. So our inactivation gates open, activation gates close like this. Mm-hmm. We reach threshold, the activation gate snaps open. Mm-hmm. We're depolarizing, and our inactivation gate slowly starts to close. We reach the very peak, and our inactivation gate closes. Mm-hmm. And then those voltage gated potassium channels, they fully open. And we're going back down, we're repolarizing. We hit around threshold again, and it just snaps and resets.
Okay.
So that's why we literally can't get another action potential, because those voltage gated sodium channels, they're locked in that position. That inactivation gate is locked in place until they reset.
Okay.
So as soon as we get past that point, all this chunk of hyperpolarization and stuff, that's our relative refractory period, where we potentially can have an action potential occur. We just need a bigger stimulus.
Okay.
And that was a lot of information. Does that all make sense? Any questions about that?
No, I think I'm good.
Same.
I don't think I brought my water down here. That's okay. Next question. Which of the following best describes the hyperpolarization phase of an action potential? The membrane potential returns to its resting state. Nope, because we're going way past the resting state. Potassium channels are closed. Sodium channels are open. Again, sodium channels are only open during that depolarization side of things. So not that. The neuron is more likely to fire another action potential. Heck no. We just talked about that relative refractory period. It's way harder to get an action potential to fire. The membrane potential becomes more negative than the resting potential. Right there is our answer. What is the purpose of the refractory period? I got ahead of myself. What is the purpose of the refractory period following an action potential? To allow the neuron to rest before firing another action potential, to prevent the neuron from firing another action potential, to increase the speed of action potential propagation, or to increase the sensitivity of the neuron to neurotransmitters. And this one is going to be, we talked about this, it's going to be to prevent that neuron from firing another action potential. Because what happens is, if we do get repeated action potentials, so let's say, and you'll see this, you'll talk about this kind of in lab and in other situations. Let's say we did get an action potential, right? We had action potential. As soon as we hit threshold, action potential, action potential, action potential, like this over and over and over again, repeated. All of these should be the exact same height, but I'm not a perfect artist. So all of these should be the exact same height. This, especially if it's going to a muscle, this is called tetany. You ever heard of a fun condition called tetanus?
Oh, yeah.
Yeah, so tetanus forces muscle contraction, and you get forced action potentials that fire immediately one after another with no break in between them, which forces muscle contraction and causes a severe spastic muscle contraction that can actually pull muscles off of bone or break bone, all that kind of crazy stuff. That's what the issue with tetany is, with tetanus. That's why we get a tetanus shot. The what's that bacteria name? Tetrasporidium, I think. Tetanus bacteria. Clostridium, that's what it is. Clostridium tetani. You will learn about that guy as well in micro. Kristen, I think if you've probably already seen that one in micro.
Have.
Yeah, the Clostridium tetani.
Talking about Clostridium.
Oh yeah. A note about starting micro. Micro starts the journey of no longer being able to watch your lectures in public, because you'll start to get into STI stuff, and almost every try from here until graduation, you're going to have some kind of presentation at different points of time, either like of genitals, of STIs, of other stuff that if you're looking at it in public, you're gonna get some really weird looks. So
Yes, you are.
yeah.
That's good to know. Don't
That's
go to
why I always put
Starbucks and
my
watch
headphones
lectures.
on mute.
Yeah.
Lectures on headphones.
Yeah, you'll see
Okay.
it gets kind of, especially when you start studying for boards and like huge sections are literally just look at all these genital warts. It's like sweet.
Just what I wanted to do.
Yeah, just what I wanted to do on my Saturday. Look at warts and genitals. Okay. Next question, we already talked about this as well. Which of the following is indicative of the absolute refractory period? So the neuron is hyperpolarized. So in this chunk, really, remember we talked about the hyperpolarization phase is more of the relative refractory period. The neuron is more likely to fire another action potential. No, it is unable to fire another action potential. The neuron cannot respond to another stimulus, no matter how strong. That's our beautiful answer that we're going to go with. There.
Oh,
I guarantee you, absolute refractory period, relative refractory period, depolarization, repolarization, hyperpolarization, resting membrane potential, all of these guys, like straight kind of definition / a little bit of the application portion of like which gate is open, which gate is closed, what's happening during this time. All of those are very common test questions. Super important to understand. Again, I'm going to reiterate this. This whole graph, super important to understand the process here, because this is kind of the base that sets you up for a lot of things you see in the future. So make sure we build off of this a lot. So use the picture that I put in there. I recommend drawing this out yourself, like drawing a really nice one. I have one. I don't know where my school stuff is. I have one laminated. I laminated mine where I wrote it all super, super pretty, super nice. And then I laminated it so that I wouldn't ruin it. So you use this and this will keep coming back. And then last question for this chunk, what is the significance of the relative refractory period? It allows the neuron to fire another action potential with a stronger stimulus. That right there is not a great question. I don't love the way that the answer is worded, but that is what allows it. Having within the relative refractory period, we will allow another action potential with a stronger stimulus. So that's the main significance of it. All right. Any concerns about action potentials themselves?
the graph is super helpful. It's super helpful.
You're looking at the picture one that I posted? Yeah. That's like deep step-by-step, very, very specific of like every single thing that's happening. And I say in the last recording, that's kind of what I would recommend printing out. I found like a blank one and you can print it out as a full page. And a lot of like the stuff that I have written on the side, that's like the numbers, I would write, like draw a little arrow specifically to where these things are happening and write in this specific thing opens here. This specific thing closes here. This specific thing starts to close here. This specific thing finishes closing right here. Because if you have it down to that and you can redraw that graph from memory, a whole bunch of those exam 1 questions that are going to cover all this stuff is just going to be a cakewalk for you.
Cool.
Okay. Let's see these rest of these questions. Yeah, these are important too. I thought, JK, we're not done with action potential. We're still with action potential stuff. These I do this because action potential stuff is really important. Like teachers beat it to death.
Yeah.
So, what is the role of voltage gated sodium channels during an action potential. They maintain the resting membrane potential. They allow sodium ions. Real quick, they maintain the resting membrane potential. Who's responsible for maintaining the resting membrane potential?
The sodium, potassium, ATPase.
Yeah, sodium, potassium, ATPase. You might also see it written as sodium, potassium pump. Same thing. So that's not correct. Those voltage-gated sodium channels are not doing that. They allow sodium ions to enter the cell, causing depolarization. Beautiful, our word-for-word definition. They allow potassium ions to exit the cell, causing repolarization. No, these are our voltage-gated potassium channels. They prevent the neuron from firing another action potential. That's our absolute refractory period. Any questions?
Oh.
Okay. Which of the following best describes the all or nothing principle of action potentials? We mentioned this. Either it's going to happen or it's not. Okay? And again, I don't love this question. I'm going to talk about these answer choices in a sec. But action potentials are always of the same magnitude. 100% that is true. I mentioned that in our drawing. These should always be the exact same magnitude. So they cannot be of varying magnitudes. This specific question, I don't like these two answer choices. Or I should say, this one could be a potential choice, and this one is still wrong. So action potentials are generated regardless of the strength of the stimulus. That is wrong because the stimulus must reach threshold. Okay? And action potentials are only generated if the stimulus is strong enough. That is technically true, as strong enough meaning it reaches threshold. Okay. It's kind of nice that these questions aren't perfect, so that way we can kind of see some other potential answer choices to the same question. Okay. What is the role of the myelin sheath in action potential propagation? First question for you two to answer. What is a myelin sheath?
It's the coating around the nerve.
Yeah, what's it made of?
Protein.
So the myelin sheath is mostly made up of fat. So it's kind of fatty protein that's wrapped around the nerves. And there's two different cells that are responsible for the creation of myelin. In the central nervous system, meaning the brain and the spinal cord, we have these cells called oligodendrocytes. Do those sound familiar?
Yes.
Oligodendrocytes, you have a main cell body, and they shoot off a whole bunch of branches to myelinate different cells. So see how it's kind of branched all, and it has a main cell body and nucleus, and it shoots off and myelates a whole bunch of different parts of cells, like this guy right here. See that?
Yeah.
This is only in the central nervous system. In the peripheral nervous system, we have Schwann cells. Schwann cells only do one individual section of myelination. They wrap, and there's some really cool, like, this is a good picture of it. See how they wrap over and over and over and over again. Their job is similar to that of a wire, like the rubber coating around a wire. It allows for the signal to travel a lot faster, for the electrical signal to travel a lot faster through our nerves. You can think of the nerve as like the cable or the like the wire running through. And it also helps us prevent us from losing signal to the outside. So we have oligodendrocytes, and then in the PNS, we have Schwann cells. Okay, remember that's going to come back a lot. Oligodendrocytes versus Schwann cells. A little bit here in physiology, but a lot more in neuroscience, pathology courses, that kind of stuff, because we're going to talk about a lot of different conditions that affect these different kind of cells and how they affect them. Okay, so keep that in the back of your mind. So the myelin sheath, as we talked about, it allows for faster propagation of action potentials. It allows it because it insulates it and allows it to go way, way faster. Here we go. Here's a good picture. A little bit more vocab. I'm not sure if Dr. Tate will get into this, but the previous teacher did a lot. So we have our nucleus, our cell body. The cell body is also called the soma, S-O-M-A, the soma. The axon, where the signal travels across, where the Schwann cells wrap around as the myelin sheath. In between the different chunks of myelin sheath, we have what are called nodes of Ranvier, or Ranvier, however you want to pronounce it, it's fine. This is where this is how the myelin sheath makes the signal travel faster. Rather than having to completely travel all the way down the axon, it can jump. So this part right here depolarizes and does its thing. And then the signal can quickly transfer all the way here. And then this depolarizes and sends the signal. It spreads, depolarizes, spreads. And so it can kind of jump. Rather than the whole length of the axon having to depolarize, it can jump from space to space and move a lot quicker. And that's the job of the myelin sheath, nodes of Ranvier, all this kind of stuff. There's a specific name for that jumping. It's right here, saltatory conduction. There it is. It's called saltatory conduction when it jumps from the nodes. And which of the following is true? It occurs only in the myelinated neurons, and it is one that it's going to be faster than the continuous conduction. I believe, make sure. Yeah, it's faster than continuous conduction. Any questions about all that stuff that I just walked through?
Nope.
That was a little baby crash course of neuro. So you'll see a lot more of that in the future. Are either of you thinking about doing any of the master's programs?
I am.
I might, but I have 2 master's degrees already, so.
I mean, it's scholarship and it's free. So, I mean.
Yeah. Well, I mean, I might. I don't know.
I'm in the neuro masters right now. And I like it. There's a lot of really, really cool stuff that you learn in the master's programs. Parker does offer an MBA master's degree.
That's the one I'm thinking about doing if I do one.
Yeah, there's my CBI doc did the MBA through Parker, and he said that he learned a lot of really good stuff. And you can do a lot, even like non-chiropractic stuff, with an MBA. So.
Yeah, that's the direction I'm leaning if I do one, since I already have 2 others. Yeah.
Yeah. Keep this in your mind for the future. You typically start the master's programs around try 6. However, the course load for those classes will carry you an additional trimester after you graduate from the DC program. So if you want to do the master's program, try 4, figure out who to contact for that, and see if you can start it early. Because if you can, then it's easier to, I'm doubled up on classes right now, which is kind of a pain in the butt. If you can figure out starting it early, then, you know, much easier as far as like graduation and stuff goes. Okay, back to wonderful physiology. During the relative refractory period, a stronger stimulus is required to generate another action potential because sodium channels are inactivated and potassium channels are closed. Not quite. We talked about this where the sodium channels have been kind of reset and the potassium channels are closing, almost closed at this point. Sodium channels are closed and potassium channels are open. That's going to be our best answer. The sodium channels are open, potassium channels are closed. No, both the sodium and potassium channels are closed. That would be resting membrane potential. So yeah, so sodium channels are closed and potassium channels are open during that relative refractory, during most of the relative refractory period. So, which of the following ions play a major role in depolarization, repolarization of a neuron during an action potential? Sodium and potassium. Later on, our next chunk of material, we'll talk about the neuromuscular junction and muscles. Neuromuscular junction and muscles, we add in calcium and acetylcholine into the mix. So we'll keep building. It looks very, very similar. That whole process looks very similar-esque to action potential stuff that we're looking at right now, with a couple of extra little steps in there. So we'll walk through that next week. We'll go dive into that kind of stuff.
Good.
What is the primary function of the sodium-potassium pump during and after an action potential? To maintain that resting membrane potential, that sodium-potassium pump is going to come back 8 million times. You're going to see it all the time. Which of the following is not a phase of an action potential? Well, we start with depolarization, and then we repolarize, which leads us to hyperpolarization. So we don't have a polarization phase. Sometimes you'll see that during depolarization, once it goes past 0, some graphs will call that overshoot. Sometimes it's asked about, sometimes it's not. So I wouldn't worry too much about that. I think I included it in, I included it in the picture graph that you put in the chat.
Cool.
Which of the following statements about action potentials are true? Action potentials are graded responses. Action potentials travel in both directions along the axon. Action potentials decrease in magnitude as they travel along the axon. Action potentials are all or nothing responses. We've said this a couple times. They are all or nothing responses. Either they happen or they don't. They are not graded. Graded is when we talk about grading, we're more referring to kind of muscles and like the electric signal in muscles that's generated based on how much force we use. So remember that the action potentials are going to be uniform height. They're always going to be and look the exact same. Action potentials, they're only going to travel along one direction of the axon, whichever one. We have what are called, we have efferent and afferent. Do you remember those words?
Yes.
Yep.
Yeah. Efferent is brain to body. Afferent is body to brain. So depending on the type of nerve or whichever nerve cell you're talking about, they're going to have one direction they send those signals. What is the main difference between an action? Oh, sorry. Action potentials decrease in magnitude? No, they always stay the same. Okay. Next question. What is the main difference between an action potential and a graded potential? So the action potentials are all or nothing responsible. Graded potentials vary in magnitude. I went ahead and I answered the last question when we were talking about the other one. So the graded potentials have different magnitudes. Action potentials are the all or nothing. Again, graded potentials, we'll look at those when we talk about muscle stuff.
So
Any
action
questions?
potentials are like always nerves, pretty much, yeah?
We'll talk about them being transported along muscle cells as well.
Okay.
So the action potential itself is an electrical signal that determines like when the certain gates of the voltage gate is open and close.
Okay.
How the signal travels. So right now we're looking at it only in the terms of nerves. Next chunk of material looks at, okay, we have an action potential that travels along a nerve. Now, how do we communicate that signal to a muscle?
Okay.
So, and that's what we'll look at. We look at something that's called a neuromuscular junction, where the signal is passed from a nerve to a muscle to something called the sarcolemma, which is like an outside, it wraps around the muscles. And that's like where it has a membrane and it's going to continue to carry the action potential signal down into the muscles, and then the muscles are going to react accordingly.
Okay.
As well, yeah. So this whole kind of the action potential, we'll look at different ones. We'll look at a nervous cell one. We'll look at a skeletal muscle one. So there'll be another graph that we'll look at similar to this. There's going to be another one for skeletal muscle, another one for smooth muscle, and then another one for cardiac muscle.
Okay.
So we'll look at those 4 in this course.
Cool.
How are we feeling? Do we want to jump into a little bit of week 2 material, or do we want to go ahead and put a pin in it and call it a night?
I think my brain's done, if I'm being honest.
Same here.
I think my brain's done.
Good job today getting through this stuff. There is a lot of material in physiology, so I think what I'm going to try and do is keep these sessions more like this, more like the question-based kind of thing, just so that we get a lot of practice with these questions. And at the beginning as well, like when you have your lectures this week, if you run across quiz questions or other like lecture type questions or anything like that during the week, save them, write them down, and bring them to these meetings, so that way I can look at them and be like, okay, what's what, and get a little bit of a better idea kind of if Dr. Tate is covering other things that I need to make sure that I hit. We can look at that as well.
That's good.
Sweet. Well, thank you guys for coming, for showing up. And I hope you guys have a good rest of the first week of the try. I know it's a lot.
I'm trying not to die, but it'll be all right.
Surprisingly, the one I'm having a hard time with right now is growth and clinical imaging.
Clinical imaging is going to be harder than I expected it to be.
In the beginning, it is. It really is. Clinical imaging 1, is that Dr. I think she got married. Is it Dutton, Norton, or Zapay?
Norton.
I don't
Norton?
have either. I have Graph.
Oh, Dr. Graff. Okay. Dr. Norton, either you love her or you hate her. I loved her. I thought she was a hoot and a half.
I would say she's a hoot. She's the
she's a little eccentric, but like if you just lean into it and have fun, you'll have a lot of fun in the class. And
her humor is very similar to mine, so I think we're gonna
yes.
get along great.
Oh yeah, a little bit of like a little dry, but a little bit like dark humor-esque as well.
A little dry, a little dark, and a little bit self-deprecating. Yeah, it's like.
Oh yeah, yeah. Very much so.
The one thing I'm having a hard time with Clin-Imaging 1 right now is the images Dr. Graff has for our lab aren't the clearest. So it's like,
yeah,
it's fighting to find what you're looking for. I'm like, am I doing this right? Because
they do that for a reason. It's because the board exams have not updated their images in like they're still using images that were taken like in like 1995.
Okay.
That are just super crappy.
Yeah.
So
I was gonna say, because I feel like Dr. Norton's kind of doing the same thing, but like I figured it was for a reason. So
same here.
It's because of the board exams and because of like the textbooks as well. Some of the textbooks don't use super updated imaging. So like the technical academic imaging that they're supposed to use is still that a little bit outdated. Yeah, it's a little bit of that outdated kind of stuff. But
yeah, because I'm having a hard time figuring out which points which. Like I go back to her lectures. I've gone back and watched lecture like 3 times now, and I'm like, I know what she's pointing to, but when I go to look at the lab picture, I'm like, that's not the same.
Yep, a lot of it is really just staring at a lot of x-rays.
Yeah, well, I can't figure out is like, I get it, the teachers want us to be able to submit it and it be right, but like with all our other previous labs that were online with that program, we could at least check our answers to make sure we were right.
Yeah, and if you have concerns, questions, like reach out to the professors.
All right.
And like
I will.
Yeah, imaging I have found is very much like Dr. Giuseppe says, and that it's like rub your eyes and hallucinate, and then you'll see it. Like,
and yeah, they said I think the better answer is you just need to stare at a crap ton of x-rays. Like I look at x-rays right now at my CBI. I look at probably 5 or 6 a day at least, and it's definitely, and I say 5 or 6, I say 5 or 6 patients, which a good chunk of them have like 15 to 20 x-rays and an MRI and a CT. So
the sad part is I can read MRIs and CTs, but I struggle my ass off with x-rays.
Yeah, it just takes time. It just takes practice. The more, and that's another thing with try to, like that fatigue that you're starting to feel today, like there's gonna be a lot of it.
I know.
It's just kind of, yeah,
I'm not worried about it. I'm just,
caffeine is about to be my best friend.
Yeah, I hear you. You guys, especially those of you who are on campus, like,
dude, I'm dying. I'm dying.
If you guys need any additional help, tips, tricks, anything like that, please let me know.
All right.
I will say, as much as you can, make tutoring for Phys 1 and Biochem 2 a priority, because I promise you guys, Biochem 2, especially with how much you guys have to do, Biochem 2 quickly can become a back burner class, and then the test hits and everybody craps their pants.
Yeah, that's what I'm worried about with that class, because I'm like, I haven't even opened it except for course certification, and I'm like, oh crap, like I gotta do something.
Yeah, so, and I have, let me check my playlist for Biochem 2. How much did I get done? I have chapter 2, chapter 3, chapter 4, chapter 5. I have up to chapter 7 recorded in Biochem 2.
Cool.
So there's at least the first handful of weeks, you're going to be good with watching those videos. It's where I go through the whole book, and then we'll be doing the Linus learning questions. So I promise we'll get through a lot of that.
Cool.
All right, you guys.
I'm gonna go stuff my face now.
Get out of
here.
Like,
yeah, it's dinner time.
I'm gonna go get Taco Bell because I want a Baja Blast.
Nice.
All right, have a good night, you guys. Take care.
Good night.